everyone, now we will start discussion on the topic air pollution control part 3. In part 1 and part 2 of air pollution control, we have discussed on gravity settlers and then packed bed and electrostatic precipitator, and now we will discuss on cyclone separator. So, as we have seen in case of gravity settlers, the gravitational force plays a significant role to remove the particles from the settler. Here in case of cyclone, we will see that a centrifugal force will be important to separate the particles in the system and the device. As shown here, see here the particle laden gas is getting entry into the system, that is called the cyclone separator. So, here it is getting some circular movement and the gas will be moving inside the cyclone, which has two part, that is upper part and lower part. The upper part is cylindrical and lower is a conical part. When the gas is entering into it, it will be getting a circular movement as shown here, and the particles, the bigger particles will be separated easily. Actually, the particles will move from the center to the outer side, and when the particle will reach to the outer side, that is it will arrest here, its velocity will be radial velocity will be 0 and particle will fall. So, this is the mechanism for the separation. Now, one thing very important here to see that the diameter of the lower part is gradually decreasing. So, cylindrical part is converted to conical one. So, the finer particles will be moving downwards and may be separated. So, bigger particles will be separated here, smaller particles will be separated here, and it may be possible that very fine particles, those are may not be able to be separated. Their particle size is so small, then they are not getting sufficient centrifugal force and radial velocity is not sufficient. So, that they will not be able to move towards the outer side of this vessel, and as we have put one fan at the top. So, there will be some very less vacuum, small vacuum. So, this gas will be going out. So, very fine particles may go out with this gas stream. So, this is the working of a cyclone separator, and you see the high speed rotating air flow is established within a cylindrical or conical container called a cyclone. So, here we can have two considerations. One is the particle size, the size of the particle which can be separated, that is minimum particle size which can be separated in the system. Otherwise, if it is lesser than that value, that will not be separated. Another is there are number of particles and a range of particles are there. So, there will be one particle size that 50% of the material will be separated, which are above that particle size. So, that is the your cut point or cut diameter as per the definition for cyclone separator. And for the separation of a particle, its radius must be equal or more than 0.2 do. So, this is the do through which the gas is going out from the separator. Now, we will see different dimension or typical dimension of a separator, and in case of cyclone separator, the different dimensions like say height, total height and cylindrical height and your conical height, and then the inlet duct length and width. Okay. So, all those things will depend upon the diameter of the cylindrical part. So, what is the diameter of the cylindrical part? On the basis of that, the other lengths will be decided. So, this table shows us say this is different nomenclature, and for conventional separator and high efficiency cyclone separator, what are the relationship? Basically, d the cyclone diameter, that is the basic parameter. So, if d is 1 unit for conventional and for high efficiency in both the cases, then entrance height. So, this is the entrance height through which the gas is entering into the separator, that duct will be having some height. So, that height is A, and B is entrance width. So, it is not shown here, here we can see the B. So, when it is going, so one will be your say this is the duct. So, this is our B and this height is your A. So, the height and B we are having. So, entrance width that will be 0.25. If one is our one unit is our D, then B will be 0.25 and D will be 0.5. That means, if it is D, so then this will be D by 2, then that will be D by 4, and S is the exit length. That means, through this duct the gas will be going out. We have a fan at the top. So, it will blower at the top. So, this will be creating very low vacuum inside this. So, this dimension DO, that is exit diameter, that will be your 0.5, that is again D by 2, and exit length x from S this will be 0.625. So, this A we have 0.5. So, this difference will be there, that is equal to D by 8, basically this equal to D by 8, and total S is equal to 0.625. Okay. Now, H is the cylindrical height. So, cylindrical portion height is H, and that is equal to 2, that means 2 D, and H is the overall height, that is equal to 4 D. So, we can say this part is also 2 D and this is 2 D. So, total is 4 D. So, this one. Now, B. So, dust exit diameter. So, this may be arbitrary or it may be like this 0.2, that means D by 4, and in other case high efficiency 0.375. So, this is for conventional and these are for high efficiency cyclone separator. So, these are the very typical dimension of a cyclone separator, and here this beta is 180 degree angle. That means, gas will enter here and it will rotate 180 degree, and again it will get a circle, it will get a circular movement and will move, just shown in the previous diagram. So, this way the cyclone works, and now we will see the minimum particle size for separation. Now, if we think about different forces working on the particle in the separator, then we will see that one centrifugal force is working on it, on the particle in the outer direction. So, that is centrifugal force, and certainly one drag force will be in the opposite direction, that is in inward direction. Okay. So, then centrifugal force we know that m v theta square by r, and v theta is tangential velocity, and v theta is tangential velocity, m is the mass of the particle and r is the radius of rotation of the particle. So, if any particle is there any position from center to this position say, so this equal to r. So, this will be having this relationship, that we know it very well, and a drag force will be working on it. This particle may be at the outer, it may be any place in between. Okay. So, that will be the r value will change, and then drag force will be 2 pi mu g dp into V r, when V r is the radial component of the velocity of the gas. So, this direction what is the velocity, that is called V r, and then mu g viscosity of gas and dp diameter of the particle. Now, at equilibrium these two forces balance each other. So, in this case gravitational force will also be there, but that will be not that much, it may be ignored. So, at equilibrium these two forces balance each other. So, m v theta square by r, that is equal to 3 pi mu g dp V r, we are getting V r is the radial component of the velocity of gas. So, we can get m that is we can get v theta square by r is equal to 3 pi mu g dp V r divided by m, this expression, or we can write, if we consider this the particle as a spherical particle. So, m we can get by knowing the particle diameter. So, that is volume of the particle diameter into density. So, by replacing that that volume 4 by 3 pi r cube. Hence, for spherical particle this will be V theta square by r is equal to 18 mu g dp square V r into rho p. So, this is the relationship. Already we have discussed this relationship in case of settling chamber also. Now, laminar gravitational free settling velocity, as you know particle is inside the cyclone, centrifugal force is working on it. So, drag force is also working on it, but still there will be some forces, gravitational forces that will be working, but we may ignore it, but in that case if we want to get the V t value. So, that V t will be rho p minus rho g into g dp square by 18 mu g if it is a laminar flow, already we have discussed in our previous classes. So, that is this is our V t, and when the density of solid is much higher than air, if the particle density is very high and air density as you know it is less. So, in that case this difference can be approximated at rho particle. So, rho p g dp square, this may be rho p g dp square by 18 mu g. Okay. So, by rearranging g by V t, that is equal to 18 mu g divided by dp square into rho p. This relationship we are getting by the definition of V t, and another relationship we have got V theta square by r is equal to 18 mu g V r by dp square by rho p. So, this right hand side term is same for these two equation, this equation and this equation, the right hand side term here and left hand side term here are same. So, what we had V theta square by r, that is equal to, we can put this one. So, that is equal to nothing but g by V t. So, by rearranging these two, putting this value as g by V t, we can get V theta square by r equal to V r g by V t. Now, three velocities are correlated by this expression, where V theta is the tangential velocity, V r is the radial velocity and V t is the terminal settling velocity. Now, this V theta value will change. The theta may be, V theta means the tangential velocity, particle may be available at any position, that is r value may vary. Okay. So, V theta, it has been shown that is a function of radius, so of rotation, radius of rotation. So, that is inversely proportional, inversely with nth power of radius, that means V theta is proportional to 1 by r to the power n. So, that will be some constant by r to the power n. This n value is normally 0.5 to 0.7, and if we take the approximation at 0.5. So, then V theta by V theta c is equal to d by 2 to the power half divided by r to the power half. What is the d is the diameter of separator, that means the particle is at the outer surface we are considering, that is maximum V theta, in that case that is V theta c, that is tangential velocity at the circumference of the separator. So, tangential velocity at the circumference of the separator, that is at distance small r is equal to capital D by 2. So, this is the, so V theta by V theta c is equal to d by 2 to the power half by r to the power half, or V theta is equal to V theta c into root of d by 2 r. So, this expression we are getting. So, it had been found that this V theta c, which is the tangential velocity at the circumference of the cyclone separator, that is almost equal to the velocity of gas, that is the, say if this is the cyclone separator, here it is getting entry and then it is moving like this. So, in that case what velocity we are having, that is equal to V I. So, V I will be having the same, if the particle is this here. So, the V theta value will be similar to that, that will be the V theta c at this will be equal to V I, but this position is inside any place, then it is not. So, only at the circumference the V theta value, that is V theta c is equal to V I. This is one approximation, and it had been found that these values are very near to each other. Now, if this is the case, then V theta c can be calculated from the mass balance. So, if G is the mass flow rate of gas, then V theta c is equal to G divided by A I into rho g, that is A I is the cross sectional area of the gas inlet. So, inlet duct cross sectional area into velocity, tangential velocity, that is the volume, into rho g, that is the mass. So, that this expressions we are getting. So, V theta, if I want to get tangential velocity at any location, so it may be at the circumference or it may be at the inside any position. So, that correlationship we have got, that V theta is equal to V theta c root over d by 2 r. So, in that case we will replace this V theta c in terms of G by A I rho g, because V theta it is very difficult to measure actually, but these are we can measure easily, these are measurable parameter. So, now you are able to convert this term into a measurable quantity. So, V theta is equal to G by A I rho g into root over d by 2 r. Now, the radial velocity V r, say here I want to get the radial velocity, that is the V r. So, how can we calculate the V r? So, again by mass balance we can calculate. Why? Because if this is the r distance, so 2 pi r, this will be the perimeter into length, the height of the cyclone. So, this will be the surface area into V r, this direction, that will be the volume, into rho a, that is the mass. So, that is equal to G. So, what is the mass of air getting entry into the system? We are assuming that the same mass is crossing through the periphery of the surface through the surface at distance r. So, that 2 pi r into h is the total surface at distance r, and then multiplied by V r, that is the volume, volumetric flow rate, and multiply it into rho a. So, that is the mass flow rate. So, this mass flow rate actually has come through the entry point, entry duct to the separator. So, then we are getting V r equal to this one, where h is the depth of the separator. Now, for the separation of a particle, its radius must be equal to or more than 0.2 of do, that is the through which the gas is going out. So, that diameter into 0.2, that should be the critical value for the separation of the particle, and do is the dia of the top outlet. Therefore, what will be the V t minimum? So, V t minimum will be this much, and how, why V t minimum will be this much? Because we have relationship V t is equal to V r g by V theta square. So, V t we have V r g by V theta square into r. So, now we will replace this V r value here, that is G by 2 pi r h into rho a, and we will replace V theta value here G by A I rho g root d by 2 r. By if we replace these values V r and V theta now in terms of these, then we can get V t, and here this r is also there, and that r is nothing but 0.2 do. If we replace this value here also, then by rearranging we will get V t minimum equal to 0.2 A I do rho g g by pi h d g. So, these expressions we are getting from this way. Okay. So, if this is our V t minimum, that minimum terminal settling velocity, then in this expression we can find that V t minimum is equal to d p minimum square into rho g into g by 18 mu g. If the flow is in laminar zone, if the flow is laminar, then this expression V t is equal to d p square into rho g into g rho p into g divided by 18 mu g. So, this is the expression already we have discussed. So, here since the V t is minimum, so d p will also be minimum. Now, this V t expressions will replace by these expressions which we are getting here, and rearranging we will get the d p expression dP, that is minimum dP, that is equal to 3.6 AI square dO rho g into mu g divided by pi h d rho g rho p into capital G to the power half. So, this is the expression for the minimum particle size which can be separated in the cyclone. Now, we will discuss the cut diameter and the collection efficiency of cyclone separator. So, here again the same thing, the two forces will be there, one is your centrifugal force outward, that is F c is equal to m v theta square by 2 r, m v theta square by r, m v square by r, and that is drag force 3 pi mu g d p v r. So, these two will be same. So, this is square. So, again if it is for spherical particle, we can get these two relationship pi by 6 d p cube rho p minus rho g, this one, this is square, and then V r is equal to this much, this expressions we get. Again we have seen that V theta is proportion to 1 by r to the power n. So, V theta into r to the power n equal to constant, that is equal to alpha, or V theta equal to alpha by r to the power n. So, n is the exponent, is dimensionless and its value is normally 0.5. Now, we are going to calculate volumetric flow rate through a curved duct of rectangular cross section. So, if we have a duct like this, okay, so then we see the volumetric flow rate and we will be trying to understand how the particles will be collected at the outer surface of the cyclone. Now, the volumetric flow rate here, that is equal to, we can get this one, we are considering very small like here. So, this is the particle, q is there. So, from the center the distance is r with the arc which is produced r, and r 1 is the entry r 1 and r 2 is the outer. So, inner and outer diameter. So, this is our duct, the particle is coming here with the q, your volumetric flow rate. So, that volumetric flow rate is how we can calculate, if we have the cross sectional area and if we have tangential velocity, then we can do. So, we have W, W is height or depth of the entrance section. So, depth of the entrance sections if we have W, and we are considering a very small radius, small part, that is a dr, we are considering a very small part, that is equal to dr. Okay, so, this is a very small. So, dr into W, that is cross sectional area, into V theta tangential velocity. So, this is the volumetric flow rate through this small duct with diameter dr. Now, if we integrate with r 1 to r 2 from this to this, so then that will give us total volumetric flow rate through this duct. Okay. So, this expressions if we can rearrange from r 1 to r 2, this is r 1 to r 2, r 1 to r 2. So, then and V theta, if we replace, V theta is nothing but we have seen alpha by 1 by r to the power n. So, alpha into W is constant now, and dr by r to the power n, r 1 to r 2, this expressions we are getting. If we integrate this alpha into W into r 2 the power 1 minus n minus r 1 to the power 1 minus n by 1 minus n, this is just simple integration. Or by rearranging alpha value, we can write alpha is equal to q into 1 minus n divided by W into r to the power 1 minus n minus r 1 to the power 1 minus n. So, what will be the V theta now then? That will be q, because V theta is equal to alpha by r to the power n. So, this is V theta is equal to q into 1 minus n divided by W into r to the power n into the same term r to the power 1 minus n minus r 1 to the power 1 minus n. And V r will be what? V r is equal to nothing, but we have some relationship, that is V r is equal to this d p square rho p minus rho g into V theta square by r, and in the denominator 18 mu g. So, this term we will be replacing by V theta value here, and V r equal to this is our V theta. So, d p square rho p minus rho g into this. So, this will be square. So, q square into 1 minus n square divided by 18 mu g was coming from the V r expressions, and then theta V theta expressions is giving this as W square into r to the power 2 n plus 1 into r to the power 1 minus n minus r 1 to the power 1 minus n to the power whole square of this bracketed term. Okay. So, this is the V r we are getting now. Now, we will see the collection efficiency. Okay. So, due to turbulence, we can assume that the particles are uniformly distributed over the cross sections at any given angle theta. So, within this angle we are assuming the particles are almost uniformly distributed here, and considering the effect of laminar sublayer next to the outer layer, and see this is our outer layer. So, here will be laminar sublayer which is very attached to it. Okay. Next to the outer edge of the duct cyclone, where all particles which enter it are captured. So, as I mentioned that particles has to come in contact with the surface of this. So, this is a very thin layer we are assuming. So, here if some particle comes, that will be trapped, okay, that will be settled. Now, if r2 d theta is the distance required, say this is our r2, this is our r2, this place to this place r2, and this is our d theta, say. So, this is our d theta. So, this volume will be r2 d theta, this distance we are assuming is required to trap the particles. Okay. So, within this surface area at the periphery of this separator, some particles will be separated. Okay. Then the fractional decrease of particles over the angle d theta can be obtained by writing a mass balance for an element of flow. So, that how, what are that mass balance? If Q is the volumetric flow rate, so volumetric flow rate into C, that is the mass flow rate, and that is getting entry to the duct, and which is going out from this, that is equal to C plus d C into Q, same volumetric flow rate, but density changing. So, C plus d C into Q, and some particles which are separated. So, which particles will be separated? That will come at the outlet sublayer. Okay. So, that will come at the sublayer, which is laminar sublayer, which is generated inside the cyclone at its periphery. Okay. So, this place. Now, then what is that collection or what is that separation? So, cross sectional area into V r into concentration. So, what is the cross sectional area? We know that W is the height and r2 d theta is our this one side. So, this r2 d theta into W is our cross sectional area. So, towards this direction, if the flow is towards the outer side, then this is our cross sectional area, and we will be multiplying with this radial velocity V r 2. Here V r 2, why? Because when the r value is r 2, then only separation will take place. So, then V r 2 and in multiplied by C. So, this is the mass flow rate for the separation of the particles or the particles which are coming at the outer surface and getting settled. So, this is the overall mass balance. So, by rearranging we can get d C by C equal to V r 2 into W by Q into r 2 d theta, and theta is equal to 0. When theta is equal to 0, C is equal to C 0, that is total particles concentration. At that time just what particles are getting entry into the separator, no decrease. So, that C 0, thus integrating we can get C by C 0 equal to exponential minus V r 2 W by Q and r 2 theta. So, these expressions we are getting, and we know that efficiency is 1 minus C by C O or for any value of theta. Okay. So, this expression is 1 by C by, so 1 minus C by C O. So, 1 minus exponential minus V r 2 W by Q into r 2 theta 1, for this theta 1 value we are getting. Now, so then V theta is equal to Q into 1 minus n W r to the power n r 2 to the power 1 minus n minus r 1 to the power 1 minus n. So, then we can calculate that W by Q is equal to 1 minus n divided by V theta into r to the power n into r to the power 1 minus n minus r 1 to the power 1 minus n. Now, we will replace this W by Q value here, and if we replace, then we will get the efficiency in terms of this expression 1 minus exponential minus V r to 1 minus n r 2 theta 1 by V theta to r 2 to the power n and r 2 1 minus theta minus r 1 1 minus n, r 2 1 minus n minus r 1 to the power 1 minus n. So, these expressions we are getting. Now, what is this? V r 2 by V theta 2, this is nothing but when the r is equal to r 2, at that time the radial velocity and the tangential velocity, this ratio. Okay. So, at r equal to r 2. So, now this is equal to, we are getting, we know by the definition of these forces, dp square into rho p minus rho g 1 minus n into q by 18 mu g w r to the power n plus 1 into r to the power 1 minus n minus r 1 to the power 1 minus n, or efficiency is equal to 1 minus exponential of this one. Now, if we put the value of n is equal to 0.5, so then that will be 1 minus exponential these expressions ultimately we will get. Now, this is the efficiency calculation. Now, how we can get the cut diameter? For that some empirical relationships are available, and if the theta 1 is equal to 2 pi n e, that is if the revolution is your n e, n is the effective number of turns of gas makes in traversing the cyclone, usually it is 6 turns it takes. So, then theta 1 will be, which theta 1 is having here, that will be 2 pi into 6. So, 12 pi. So, collection efficiency in term of the cut diameter, and that cut diameter is mentioned as dpc root of 9 mu g v and 2 pi n e v I rho p minus rho g, when the dpc is the cut size or cut diameter and size of those particles that are collected with 50% efficiency. V equal to inlet width and V I is the gas velocity, inlet gas velocity V I. So, now we will see one numerical example. A conventional cyclone with a diameter of 1 meter handles 3 meter cube per second of standard air carrying particle with a density of 2000 kg per meter cube. Using n equal to 6, determine the collection efficiency as a function of particle diameter and the cut diameter using empirical correlation of Laplace. So, we have this formula efficiency equal to this expression, and now from the discussion which we have made on typical dimensions of different parts of the cyclone separator, we can say r 2 equal to d by 2, where d is the diameter, and r 1 is equal to r 2 minus b, where b is equal to d by 4. So, this r 1 is equal to d by 2 minus d by 4, that is equal to d by 4, and w is equal to height, that is already d by 2, and theta 1 is equal to 6 times. So, 6 into 2 pi 12 pi. So, we will be putting these values here in this expression, and by expression we will be putting these expressions in this value. We are getting that the efficiency is equal to 1 minus exponential minus 1.6213 into 10 to the power 10 into dp square. So, now the first part we are asked to express the efficiency in terms of the dp square. So, now this part is solved, and if we put different value of dp, the efficiency value will change as per this graph and as per this expression. Now, the second part we have to calculate the dp. So, dpc, so cut diameter, so cut size dpc is equal to root of this. So, here we have to calculate the vi, other values are given, v values is 0.25 meter because d equal to 1 meter. So, d by 4 equal to 0.5 meter and a equal to 1 by 2, that is 0.5 meter, and a equal to w. So, V I is equal to q by a b. So, volumetric flow rate, that is equal to cross sectional area into b into that V I initial gas velocity which is entering into the system. So, this way we can get the V I equal to q by 0.5 into 0.2. So, that is equal to 24 meter per second. So, all other values are given, V I is calculated, we will put it here and we are getting the value of dpc is equal to 4.7 micrometer. Now, we will see the efficiency of cyclones. So, from this the conventional and high efficiency cyclones, if we compare the efficiency for different particle size, then we see that when the particle size is relatively bigger, then the efficiency is also very higher, but when the particle size is lesser, the efficiency is also less. And these are the generalized expressions already we have discussed. So, centrifugal force this one and drag force, and then laminar gravitational settling velocity this one, and this is dP minimum. And now we will compare different particulate removal equipment like say gravity settler, electrostatic precipitator, fabric filter and cyclone separator. We have discussed all 4, and here we can see the comparison like say typical particle size which can be separated for gravity settler greater than 50 micrometer, for ESP greater than 1 micrometer, for fabric filters greater than 0.01 micrometer, and for cyclone separator greater than 5 micrometer, and typical removal efficiency are also given. So, there all of these processes have their some characteristics. As a remark it is given, and that is for gravity settler they need large space, low pressure loss, and for ESP high initial cost, sensitive to variable dust loading of flow rates. Filters are susceptible to chemical attack for fabric filter, and for cyclone separator inexpensive and less maintenance is required. So, up to this in this class, thank you very much for your patience.